Hello, in this video let's discuss third question of today's contest. You are given an integer enums. From any index I, you can jump to another index j with the following rules. Jump to index j, which is the right side of index I, only if it is less than the present element. And we can jump to index j, which is in the left side, only if it is greater than the present element. For every index I, return the maximum value that can be reached by following any sequence of valid jumps starting at index I. Return an array where answer of I is the maximum value reachable starting from index I. And the constraints are n is up to 1 if I and the values are up to 1 in 9. So for example, we are at index I and the value at that index is x. So we can reach to right element only if it is less than the present element, which is less than x. And we can only reach to left only if it is greater than the present element, which is greater than x. So following these rules, we have to return the maximum value that can be reached from every index as the final array. So firstly, for example, we have very big array and we have to think about the maximum value, right? Because we can sort the values with respect to indices, and then we can think about the first maximum value. So if we think about this, then we can get a maximum answer for every possible index. For example, this is the big array and we have maximum value at this index. Let's assume that this is 100. So if this is 100, can we find answer for any other values right now? We have this maximum value. So from an index I, we can reach to the next element if there is less than 100. And from any index in the right side of 100, we can reach to 100 if it is less than 100. So if, for example, we are at 100 and we are at the next element, any possible next element is 3. So from 3 we can jump to 100 because it is greater. So as this is the maximum possible element, every index or every element in the right side of 100 will be less than 100. So we can straightforwardly jump from every next index to 100. And this is the maximum possible answer for every other index greater than 100, greater than this index. So we got the answer for many indices. So let's think answer for the before indices. It is not straightforward with before because we cannot jump to higher indices greater than that element. So this is the 100. So when it is possible to jump to 100 from before indices, if they are more than 100, only then we can jump to 100. But 100 is the maximum possible element. So there is no possibility that any of the before element before 100 can be greater than 100 because it's the maximum possible value. So we cannot straightforwardly jump to 100. So now what can we think of? So for example, let's say this is the very big array and we have 100 and we have many other different elements also which are less than 100 for sure, and we got all the answers for this index of answer is 100 because we can jump to 100. So for example, we are at index I. So we got the answer for this, we got answer for this also. So instead of jumping to 100, we can jump to any other index which is greater than, which is less than the present value rate. For example, this is 3. So we cannot jump to 100, but we can jump to an index 2 if it is there. Jump to an index of a value 2 if it is there. Or we can jump to 1, or we can jump to 0 also. So that we can jump to 100 again and we can get the answer. So we are at 3 and we can jump to 2 or 1 or 0 and we can jump to 100. But only if they are available. But what if every element in this is greater than 3? So we cannot jump and then we cannot find the answer. So we can find a subset of these indices answer only if they have an element with less than that value in the suffix part of 100. So in this part, if there is any element less than the value, then we can find the answer. So for example, then how can we do? So instead of checking elements present or there for these indices, let's try to find the least element in this. Why the least element? Because if we find the least element, then we can try to find the maximum subset of answers in this vector. For example, we have 3, we have 4, we have 6 and maximum value is 100, and we have 2, 6, 2, 3, 4 and so on. So if we try to find the least value in the suffix, then we can find the answer for 6, we can find the answer for 4, we can find the answer for 3 also. So if the least possible value is 2 and the least possible value is 3, if it is 2, then for which the answers can be finalized, it can be finalized for 3, 4, 5 and so on, because we can jump to 2 and then we can find. But for 3 what? are the possible values, we can find only for 4 and 3. We cannot find the answer for 3. We cannot find why we cannot find for 3, because we can jump to only less than the present element, but it is equal, so we cannot jump. So for as less element as possible, we can find answer for as maximum elements as possible. Here only we are able to find for 3. Here we are only able to find for 2. So it is better to find the least element, and then we are finding the least element, and then we can find the answer for remaining elements. But even there can be other elements also. So there can be other elements also, and again we have to do some kind of recursion to get the answer for remaining values. Why? Because for example this is 2 and we have 1 also. We have some subset of 1 and 2's, and we have many other different elements. Here we have 1 and 2, here we have 2. This is maximum value and so on. So we got the answer for all of these, but we don't know the answer for these. So for example this is 2, only we have 1 and 2. For example, if the least minimum value is 6, and this can be 3, 4, 3, 6, 3 and so on, and this can be complicated also, so we cannot directly find answer. So we have to do some kind of recursion or some other kind of optimization to get the answer for this, which will very complicate our answer. So we cannot think of this approach. So coming to next approach. So for example we are at index I. So from index I we have many other possibilities to jump. For example we are at I, so we can jump to this smaller element or this smaller element or this smaller element. So what we can think of now, so we can assume that we can try to find the answer just by going to next index, so that we can pre-compute the answers for this index also, so that it will handle when we are going to this also. So for now what we are able to think, we can think of a directed graph. Why? Because from any index we have a possibility to jump to an index, but not the reverse. So we can jump to I to next smaller element or I to before greater element. So if we try to make a graph with these edges, we can find the answer? No, because let's say this is the new graph, directed graph possible. So there are many wrong things because of this. The first thing is these are, so let's assume that we have this right. So this is the first component, this is the second component. But we assumed that reaching to next index will give the correct answer. But there is not, but it is not guaranteed, because we have 30, 20, 10 and we have 35, 20. So we assumed that we are only pairing with only next element. So 30 to 10 because this is smaller, 20 to 10 because this is smaller, and 10 to 20 because this is greater, and then we have 35 next smaller, and 20 this is greater. So this is the new graph. But if we try to observe more clearly, we are not making this as an edge 30 to 20. We are not making this. So by our assumption, we are able to make two directed graphs, two disconnected directed graphs. But the answer for final is 35, 35, 35. All are 35. Because if we try to make this edge, then we can reach 30 to 20, and then we can reach to 35. But here we are not able to make, because we are only thinking about the next one. So now we can think that for every index we can make a graph with every smaller element, but the complexity will be n square, because for every element we can't reach to next and we cannot make an edge. So even this we cannot do. So now let's come to other idea. So let's take the smallest array, right? For example, this is 2143. So if it is 2143, what is the answer? It is 2 to 4, 3. It is 2 to 4 and 3. Why 2 to 4 and 3? Because from 1 we can jump to 2. From 1 we cannot jump to 3 and 4, because they are right and they are more than 1. So for 1 the maximum answer possible is only 2. So it is 2, it is 2. For 4 it is 4 all as usual. And for 3 it can jump to greater elements at the before. So the greatest element is 4, so it can jump to 4. So the final answer is 2 to 4, 4. So let's take other example also. So this is almost similar to this, but let's add other dummy values in the middle. So there are many zeros in the middle, there are many 3's in the middle. So for this, what will be the answer? Even now the answer is same. All here the values are 2, all here the values are 4. If we able to observe this, if we try to observe this for more time, we can think of an idea. What? So why we are able to group here, why we are able to make all these 2 and why we are able to make all these 4? Because if we are sure that answer for 2, 0, all the array till 1 can never exceed 2. So for example, we are at this index 8. So why we are confidently able to make the answer this as 2, and why we are not thinking that there can be answer with answer 3, 4, 5 in the left side or right side of the array. Here 2, 1, 4, 3. Right? In 2, 1, 4, 3, this is very small array. So we can try to find all the possible ways, and then we can get the answer that the maximum possible answers for every index are 2 to 4, 4 only. The index for 1, it is 2 only. We cannot reach 3 or 4. So for small integers, we can get why we are only able to reach 2. But for bigger arrays, we cannot find why that is the correct value for sure. So we have to make some proof that this is the maximum possible value for this index to reach, and there is no possibility that any greater value than this present value can be finalized. So how are we sure that the answer for this cannot exceed 2? So in this array, even now, if we try to find all possible ways, the only answer will be 2 to 2 and so on. From any 0, we can reach only 2. So why we are sure that we cannot reach any other element greater than 2? So if we are sure about that, then we can just simply make all these 2, and then we can continue with the rest of the array. But we have to make sure that it is 2, else the answer will be wrong. So if it is correct, we have to prove that is correct. So why that should be correct here? That is because for every element in the right side of 1 is greater than 2. So let's take again. So 2, 0, 0, 1, 4, 3, 3. So this is the array, right? So from this, why we are able to make sure that there are 2 different subarrays and all the answer for this is 2, all the answers for this is 4. So why we are able to make sure? Because we are at 1, right? So we are at 1. So if we are at 1, when can answer not be 2? When can it be 3 or when can it be 4? It can be 3 or 4 only if we can jump to the greater elements with value 3 and 4, right? So only then the answer can be 3 and 4, because if the ultimate value of this is 3, so ultimately we have to go to 3 or 4. Let's assume that they are in the right. So if they are in the right, so we have to jump to 3 or 4, but the present element is less than 3 and 4, so we cannot jump. So from this we are sure that we cannot jump to intersection with 3 and 4 in the right side. So only then we are sure that we cannot jump to any other index. So we have to adjust with a higher value of 2. We cannot get 3 or 4. So why is that the case? So every element in the right. So if we check the smallest element, it will be true for other also. So we have 2, 0, 0, 1, 4, 3, 3 also right. So why we are able to make a partition here? We are able to make a partition here because every other element in the right side is more than the maximum value till now, which is 2, right? Because this is 2. So we cannot jump to 2, we cannot jump to 3 or 4 from any of these integers. Why? Because we can only jump to smaller elements in the right side, but every element in this 0, 1, 2 is smaller than every element in the right, which is 3 and 4. So now we are sure that we cannot jump from this to this. So our element, so for this the answer is 2, for this the answer is 4. So can we simplify this? Can we make this statement more clear? So for example, we got 2 subarrays, and the maximum value in this is mx, and the minimum value this is mn. So from this what we got, every element in this is less than or equal to every element in this, so that we are sure that we cannot jump to other, and we have to make all these as 2. So can we simplify? So all elements in this less than or equal to all elements in this. So can we write this as maximum element in this is less than or equal to minimum element in this? Obviously yes, right? Because if it is suitable for every element, it should be suitable for greater element also. And if it is suitable for every element here, it will be suitable for every other element here also. But if it is less than or equal to 0, and if it is maximum in all the possible in this and minimum in all possible in this, so if it is suitable for this, it will be suitable for every other possibility also, right? So here it is less than or equal to 2, less than or equal to 4. So this is correct. So if this is correct, so we are able to make a partition, And if it is correct, what we are able to ensure, so 2 less than or equal to 4, it means that 0, 1, 2 less than or equal to 3 and 4. So with one single statement, we are able to make all the statements true. Every element in 201 is less than or equal to every element in 4 and 3. So it is simply that maximum value in 201 less than or equal to minimum value in 4 and 3. Right? So why we are able to make break here? We are able to make a break here because the maximum till now is less than or equal to smallest in the next. So if that is the case, we are sure that we cannot jump to right side and we cannot update the answer. So all elements in this can have only answer as 2, and all in this have, let's think of this later. So for now we are only able to think of this. So in this we cannot jump to any of the right and we cannot update. So the answer for all of these is only 2. So only then we can make sure. But why we are not, but why we are thinking about some elements in the right? So let's assume that we have one, let's say it's the same one. So we have 2, 0, 0, 1. We have 1, 3, 4. And now let's assume that of only this part. So if we are able to think of this part, we cannot make sure, right? Because we can jump to 0, we can jump to 4. So we cannot isolate this subarray. But if we are at this position where breaking the thing according to the assumption before, then this whole is isolated. This whole is also isolated. So if this is isolated, then we can simply find the answer for this, right? Which is the maximum value in this subarray. So the main goal for now is to find the maximum element till now and minimum element after. So if this is less than or equal to this, then we are very happy because we got an isolated subarray, and the maximum value also is equal to maximum value in all of these. So we got the answer for all of this correctly. Why correctly? Because we cannot jump to any other index and we are filling with the maximum possible ever value in this. So we are sure with the correct value. So in this way we are able to complete in often, and also we are able to get the correct answer also. So sometimes we are able to make the complexity often, but the answer is wrong. What is the use? That is completely useless. So now we are able to make often, and also we are able to make correct answer also. This is what we exactly want, right? So we are able to make different subarrays we got. But what if we are unable to do? For example, let's assume that 3, 5, 2, 5, 3, 2, 1. So this is the array. So can we make it into different subarrays? No, because it is strictly decreasing. So we cannot find the partition. So now what can we do? So then we can simply fill the maximum answer possible. So we can make all these as 5, which is simply isolated subarray as a single one. So if we are unable to do, for example, we have done many other subarrays and we are left with the final one. So for the final one, we can make all of these equal to final one in the maximum value in the final one. So hope you got this. And now how to find the solution? We just got the idea, right? Where maximum possible till now is less than or equal to minimum in the next slide. So how can we do? So it is simply prefix maximum and suffix minimum. So let's say we have big subarray, big array, and we are breaking into many different subarrays. So we want the maximum value in this less than or equal to minimum value in all of this. So this is simply suffix minimum, right? So we can simply make prefix maximum vector suffix minimum vector. What does it mean? So let's assume that 3, 2, 1, 4, 3. So prefix minimum is the maximum value till that prefix index. So here till is 3, 3. And what is maximum till here? So maximum value of till before is 3 and the maximum value of 2. So which is 3. And here, what is the prefix maximum of this? The maximum value of before and the maximum value of 1, which is 3. And 4. So maximum value till before is 3 and the present value is 4. So the prefix value is 4. And similarly 4. So similarly we can find the prefix maximum and suffix minimum of all. And at every index we can find whether this is a possible index for breaking. So if this is yes, so how can I check if this is yes? So prefix of I is less than or equal to suffix of I of I plus 1. So that it means that maximum value till now is less than or equal to minimum value in the after. So if that is the case, then we got isolated subarray and we can make all of this equal to maximum value in this partition. So while we are traversing, we will make our running maximum value, where that is the maximum value till the current index in this isolated subarray. And if maximum this is less than or equal to minimum till next, then we can break So if we are breaking, we will make all of these equal to maximum index so far, and then we will find the new answer from this. So hope you got this. Let's check the code. So we are making prefix, suffix and answer, and we are making prefix maximum and suffix minimum, and then initially start is 0 and maximum is nums of 0. So start is the index and max is the maximum value so far, so that if we get an index that satisfies the our condition, then we can make all the indices in the present subarray as maximum value. So we are traveling from 0 to n minus 1, and we are finding the running maximum, which is maximum of maximum and v of I. And if so, now we are assuming, now we are finding whether I can be a part of a subarray, of a new subarray. Like we are thinking whether we can break an isolated subarray between I and I plus 1. When we can break only if prefix of I is less than or equal to suffix of I plus 1. So if this is the case, what does it mean? It means that we got isolated subarray and we are sure that we cannot increase our answer till I greater than the max value. So if this is the case, then traverse all the indices from start to I, where start is the new index of the isolated subarray and I is the present index. So we are making all the subarray equal to maximum value. So and now we are making a new subarray. It means that start is equal to I plus 1. So we completed the answer for index till I. So we are getting a new array from I plus 1. So start is I plus 1. And if start is less than I, so simply make maximum value. So this will, so just we are making sure that if we are able to make max is equal to, because we are able to make the new subarray, right? So in the new subarray, if it is less than bound, so then simply make maximum value is that value. So in this way, we are able to find the answer. So finally, after the whole, we are finding the maximum with rest of the subarray. So there may be a case that we found the answer for all of this and these two elements left. So we reached only to L minus 1. So we can compare this with this, and we can do other operations similarly here. So we can make the maximum value, and so we discussed it, right? What if we left a subarray, but what yeah, so if we are unable to break array, so it means that we reached the last subarray. So if that is the case, so simply fill by all by the maximum value. So simply fill start till n to max value. So simply written maximum value. So, and what is the time complexity? Is this n square? No. Though we have two loops, it is only n. Why? Because, so let's assume that these are the isolated subarrays we partitioned into. So we are traveling whole array and we are initializing all of this to the maximum value. We are traveling all of this and we are making all of this maximum value, all of this maximum value. So it is simply, it is of 2n, because we are traveling every index only at most once. So it is simply 2n. So from this we got the answer. Hope you got this. If you have any doubts, comment below. See you in the next video.